SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 25, and the topic of today's discussion is bending of unsymmetrical beams. Okay. So, till now we discussed about the bending of symmetrical beams. For example, we had a rectangular cross section and then we had the neutral axis passing through the centroid, and we also had y and z axis with its origin at the centroid. So, this is y axis, this is z axis, and this is your neutral axis. And we were applying moment about the z axis. So, we had m z, and you see the analysis was done assuming that the neutral axis and the axis of applied moment or the direction of the moment both were coinciding. So, basically we had assumed that the neutral axis coincided with the direction of applied moment. Which in this case is of course z axis, but it is not always the case. If you have a cross section which is not symmetrical, for example, if you have a cross section like this, so you see it is not symmetrical, or you could have a cross section like this. So, it is just a cross section of the beam and the beam goes into the paper, right. So, in this case, if you for example, apply moment about the z axis, so if this is your z axis and that is your y axis, and I am applying moment about z axis, then the neutral axis is not parallel to the z axis. Neutral axis could be actually inclined. So, in this case the neutral axis could get inclined. So, that is very interesting, is not it? You are applying moment about some axis, but the bending is happening about a different axis. See, neutral axis tells us the axis of bending. So, applied moment is in some direction, whereas the axis of bending is in a different direction. It is very interesting, and that can happen with unsymmetrical beams. So, we are going to do its analysis in today's class. Okay. So, as I said, let us suppose we have a unsymmetrical beam and say this is the axis. Okay. So, here also it is going to have that shape. And then we have x axis along the axis of the beam and y and z in the beam's cross section, which is unsymmetrical now. Okay. So, let us just draw the cross section now. suppose this is the cross section, and we have the centroid of the cross section and y axis as well as z axis. And let us just think of pure bending for now. Okay. So, to begin with, we will do pure bending. Which means we only have terminal bending moment acting on this beam. So, the bending moment is then going to be constant all along the beam, and therefore, there is no shear force. So, bending moment is constant and no shear force acts. Okay. Now, as I told you, the direction of the neutral axis is an unknown now. So, let us suppose that is my neutral axis. And the beam is bending about this axis, the tilted axis. Okay. So, if you go a distance y prime above the neutral axis, then on this green line we have found out that the strain epsilon xx was minus of y prime over r, where r is the radius of curvature. So, remember the basic geometrical construction. Since it is pure bending, the beam bends into a circle and the radius of the circle is big R, and then y prime is the distance from the neutral axis of any point in the cross section. So, epsilon xx there is minus y prime over r, and then what is sigma xx? So, sigma xx is simply E times epsilon xx, which becomes minus E into y prime over r. So, this was assuming that sigma yy and sigma zz are both 0. Okay. So, if this is sigma xx, what is the axial force in the cross section? So, axial force is then the integration of sigma xx over the cross section. Let us denote it by omega naught, and we plug it in sigma xx here. So, we have minus E over r integration over omega naught of y prime dA, and this has to be equal to 0, because it is a pure bending case. There is no force in the cross section, and likewise there is no axial force in the cross section. So, this has to be 0. So, what does this mean? So, you see y prime dA. So, we are measuring the first moment of the cross section from the neutral axis. So, this quantity is first moment from neutral axis, and since this is 0, that means the neutral axis has to pass through the centroid of the cross section. So, this is an interesting result, which is same as for the symmetrical cross section. So, in case of symmetrical cross section, the neutral axis was passing through the centroid, and even here the neutral axis has to pass through the centroid. It is just that the orientation of the neutral axis is not aligned with the direction of the applied moment. Okay. So, now let us redraw our picture. So, we again have the cross section, so that is the unsymmetrical cross section, and suppose this is the centroid, then we have now found out that the neutral axis has to pass through the centroid, and then it has got y and z axis. This is y axis, and we also have z axis. Okay. And think of any point in the cross section which is at a distance y prime from the neutral axis, but this point has got its coordinate y comma z with respect to the y z axis of the cross section. Okay. Now, first we like to write down y prime in terms of y and z, all right. So, we have to do some geometrical construction. Okay. So, we can see that the vertical red line and this horizontal red line. So, the horizontal is z and the vertical is y, is not it, because the coordinate of the point is y comma z. All right. Now, let us do some extra construction. So, think of this line, okay. We can actually zoom this diagram so that things are more clear. So, we have y axis, z axis, and then the neutral axis is here, and suppose that it makes an angle beta from the y axis, and any point has got its coordinate y comma z, and the distance from the neutral axis is y prime, okay. And then these lines, their values are z and y, okay. And so, we are going to do some extra construction now. So, think of joining these points through red dashed lines, okay. Now, you can see that as this angle is beta, this angle also becomes beta, and that means this angle right here is 90 minus beta, okay, because we have a right triangle over here. Now, what can we say about this distance? So, in this right triangle we have 90 minus beta angle. So, this distance becomes y times cosine of 90 minus beta, which is y times sine of beta, right. And what can we say about this distance? So, that distance and this distance, they are same, and if we focus on this triangle, then this angle is 90 minus beta, and this side is z. So, that means this side becomes z times sine of 90 minus beta, which is z times cosine of beta. All right. So, now what can we say about y prime? So, y prime is then y times sine of beta minus z cosine of beta. Okay, so that is an important result. Now, with y prime known in terms of y and z and the inclination beta of the neutral axis, we can come back to our epsilon x x. So, epsilon x x, as we know, it is minus of y prime over r, and so this becomes minus y times sine beta minus z cosine beta divided by r, and then sigma x x is simply E times epsilon x x, right. Now, let us try to find out what is the moment about the centroid of this normal stress distribution, okay, because that is going to generate the resultant moment, and that should be equal to what is the moment in the cross section. Okay. So, the moment in the cross section because of bending stress sigma x x is simply going to be integration over the cross section, then the arm of the point y comma z. So, that is y j plus z k relative to the centroid cross product sigma x x I, is not it, because the normal stress is along the x axis, and then we plug in the formula. So, this becomes, and then we also have d A, right, sigma x x d A. So, this is y j plus z k cross product E over r times z cosine beta minus y sine beta I d A. Okay. Now, let us work out the cross product. So, this tells us that the moment about the centroid, which say it is O. So, that is equal to again integration over omega naught. First, let us do the j cross I. So, j cross I is minus k. Okay. So, we get y square sine beta minus y z cosine beta into k, and of course, we have E by r outside because it is constant for the cross section, and then k cross I is j. So, we have plus z square cosine beta minus y z sine beta in the j direction, and this whole thing with an integrate in the cross section. All right. So, that is the moment. So, once we do the integration, then what are we going to get? So, we have E over r into, then have a look at this, we have integration of y square d A. What is y square d A? That is simply I z z, the second moment of cross section area about the z axis, is not it. So, I can write here that integration of y square d A, that is I z z, integration of y z d A. So, that is the mixed moment of area and this is I y z, whereas integration of z square dA, that is I y y, the second moment of area about the y axis. If we plug in these definitions here, we simply have I z z sin beta minus I y z cosine beta in the k direction plus I y y cosine beta minus I y z sin beta in the j direction. So, that is the total moment, and supposing that we are applying, let us say, m y and m z in the cross section. So, in that case this part is m z, whereas this part is m y, because these two parts are the moments about y and z axis, and since that will be known to us. So, we can equate this quantity to the knowns m y and m z. So, we get m y equal to I y y cosine beta minus I y z sin beta times E divided by r, and 1 by r is also the bending curvature. So, we could write it as curvature kappa, and likewise m z is I z z sin beta minus I y z cosine beta into E times the bending curvature. Okay. Now, what are the unknowns here? You see, beta, the orientation of the neutral axis is an unknown, and the curvature kappa is also an unknown, and then we also have two equations. So, solve these two equations to obtain beta and the bending curvature kappa. For example, let us try to obtain the beta. So, what we can do is simply divide the two equations, and then we have m y over m z equal to I y y cosine beta minus I y z sin beta divided by I z z sin beta minus I y z cosine beta. Okay. Suppose that we are only applying moment about the z axis and moment about the y axis, suppose it is 0 in the cross section. So, let us see what happens in that case. So, this would imply I y y cosine beta minus I y z sin beta is equal to 0, which further implies that tan beta is equal to I y y over I y z. Okay. So, with this formula you can get the inclination of the neutral axis from y axis. Now, you see, in the last two classes the cross section was symmetrical. So, we had, for example, the rectangular cross section, now whenever you work out the mixed moment of area for symmetrical cross section, then it is always 0. You see, in this case since it is symmetric about y and z axis both, so they are also the principal axis, and in the coordinate system of principal axis the mixed moment of area is always 0. So, in this case I y z is 0. Okay. Now, plug in I y z 0 here, then what do we get? That tan beta is infinite, which means beta is 90 degree. So, that means the neutral axis makes an angle of 90 degree from y axis, right, and this is what we also had earlier, that the neutral axis was coinciding with the z axis, isn't it. So, we have neutral axis coinciding with the z axis, because it makes an angle of 90 degree from y axis. So, it perfectly matches with our earlier result, but then here we have more general formula for the inclination of the neutral axis. Okay. So, we can box this formula. Okay. So, once we have beta known, then we can plug in beta in any of the two equations here and also obtain the bending curvature, right. For example, upon using the first equation here, the curvature kappa is simply m y divided by Young's modulus E into I y y cos beta minus I y z sin beta, and then beta you obtain from the above equation. Okay. With curvature and the inclination beta known, we can then also obtain sigma x x. So, what is sigma x x? So, we know that this is E times epsilon x x. So, it is minus of E times y prime over r, or we could also write it as minus of E into y prime into curvature kappa, all right, and then we plug in the formula for kappa from here, and this tells us that sigma x x is minus m y into y sin beta minus z cosine beta divided by I y y cosine beta minus I y z sin beta, all right. If we also plug in beta in this formula, then our final result looks as follows. So, that is m z into y times I y y minus z times I y z plus m y into y times I y z minus z times I z z divided by I y z whole square minus I y y into I z z. So, it is a quite tedious formula. Just compare this with the formula for the symmetrical cross section. We simply had sigma x x equal to minus m z into y over I z z. So, that was for symmetrical cross section. With only m z present. Okay. let us just try to see, can we obtain this simpler formula from the general formula. So, this general formula is for unsymmetrical cross sections, but suppose that we choose our y and z axis so that they are aligned along the principal axis of the cross section. Okay. So, let us suppose y and z axis are aligned along the principal axis. So, that means we have this cross section and we first have to find out the principal axis. Suppose that it is like this. So, that is your y axis and z axis. So, we align it along the principal axis and then the moment that is acting in the cross section. So, we may have moment acting, let us say, in this direction. So, that is the moment, and then we can resolve this moment along the principal axis. So, we get m y and m z. Okay. Now, let us see what happens to this formula now, because the y and z axis are the principal axis. This also implies I y z would be equal to 0. So, plug in I y z equal to 0 in the general formula and sigma x x would become. So, we come back to the general formula and we say I y z is 0. Okay. So, if you work out, we are going to get minus m z into y over I z z plus m y into z over I y y. So, that is the formula that we get. So, now you can see this resembles with our earlier result. Now, suppose that m y is 0, then this is exactly what we had earlier, is not it? An interesting point to note here is that the first term comes with a negative sign, whereas the second term comes with a positive sign. So, why is that happening? So, to understand this, we can simply have a look at the cross section. So, suppose that this is the cross section and we have y axis and z axis. Now, when we apply moment about z axis, then the bending is such that the positive y side is under compression, whereas the negative y side is under tension, right. So, we have this beam and in the cross section we have y axis and z axis. So, when you apply moment about z axis, the beam bends in this way. So, the top side gets under compression and the bottom side gets under tension. Therefore, we have a negative formula when m z is present, because the positive side has to be under compression. Now, think of applying moment about y axis. So, when we have moment about y axis, so what is going to happen? So, when you apply moment about y axis like this, then your beam bends in this way, it curves towards me. So, in that case, the part of the beam on the positive side of the z axis, which is towards me, that gets under tension, whereas the part of the beam which is away from me on the negative side of the z axis, that gets under compression. So, since the positive side is under tension, therefore, in the formula with m y we have plus sign. Okay. So, another interesting point to note is that even though the cross section is unsymmetrical, if we apply moment along the principal axis, then the formula for sigma x x is really simple, right. It is as if the cross section is symmetrical. So, I can make that remark here. Even though the cross section is unsymmetrical, if we apply moment along the principal axis, the bending happens as if it is a symmetrical cross section. Which means that the formula for bending stress is just like the one for the symmetrical cross section, and further that the neutral axis is then aligned with the direction of the applied bending moment. Alright, so this was about pure bending. Now, as earlier we also discussed non-uniform bending of beams. So, let us also talk about non-uniform bending of unsymmetrical cross section. So, let us just have some remark on this. So, this means we also have shear force present in the cross section. So, shear force is present and bending moment is varying. Now, let us have a look at the cross section. So, that is the cross section, and supposing that this is the neutral axis, and then we go a distance y prime from the neutral axis and look at this line. Now, recall that in our earlier derivation we had assumed that the shear stress was uniform along this line, right. So, when we took a line parallel to the neutral axis, we assumed that shear stress does not vary in that line, and that is how our analysis got simpler. But can we do it now? So, can we say that shear stress is uniform along this line? We certainly cannot say this, because in that case at the periphery of the cross section the shear traction would not be tangential to the cross section. So, remember in the last class we are working out circular cross section, and there also we could not really say that the shear stress would be uniform along this line. And what was the reason? That was because if we take it uniform, then the shear stress will have a component in the radial direction, which violates the free surface condition. So, whenever we have a beam, whether it is symmetrical or unsymmetrical, if the lateral surface is free, then along the periphery of the cross section, the shear has to follow the periphery, and that is again coming because of the free surface condition. If you are not applying anything on the lateral surface of the beam, then the shear stress in the cross section has to be along the periphery of the cross section, and that is only for the points near the periphery, but within the cross section, like at these points, the shear stress can have any direction, but close to the periphery of the cross section, they have to be aligned along the periphery. Okay? And if that is the case, you come back to this unsymmetrical cross section, and again we get the violation. So, we can no more assume that the shear stress is uniform along the green line. We will not get any analytical result because of this. So, you can write here, we will not get any analytical result due to this complication. Okay. But there are some analytical results for a different kind of cross section, which is thin and open cross section. So, let us talk about shear stress distribution in thin and open cross section. So, shear stress distribution in thin and open cross section. I will tell you what do each of the two terms mean, thin and open. So, it is the keyword here. So, if we have a cross section like this, so it is not a beam, it is the cross section of the beam. So, the thickness of the beam is really small. So, this thickness T is very small. So, therefore, it is called thin cross section. And why open? Because this is not closing. If we had a circular cross section, then this is a closed cross section. So, it is closed. So, we do not want to discuss closed cross section, we are only talking about open cross section, but also at the same time thin. So, this is also an example of open and thin cross section. And what is interesting about thin cross sections? You see, if it is thin, as we just made a remark here that the shear stress has to be along the periphery of the cross section at points which are close to the periphery, is not it? So, that means if it is thin cross section, then certainly the shear stress along the points which are close to the boundary of the cross section. So, it will be aligned along the boundary and likewise even on the other part of the boundary, but within the two boundaries the shear stress need not be aligned along the boundary. But if the cross section is really thin, then there is no space within the boundaries, and then everywhere in the cross section shear stress just gets aligned along the boundary. So, the nice thing about thin cross sections is that we do know the direction of the shear stress, that is, it is flowing along the cross section's boundary. Okay. So, even within the boundaries it is going to be aligned, because there is no space for variation. And then it is going to flow from one end of the cross section to the other end. If it is a closed cross section, that is no more going to hold. So, here for closed cross section shear stress will not be flowing in a unidirection, but for open cross section it always flows from one end to the other end. So, that is very interesting, and this makes our analysis easier. So, even for this S shaped cross section the shear stress is going to flow from one end to the other end. It could be that here it is flowing in the other direction. There are two ways, right. It can either start from point A to point B or from point B to point A, but we can always say it is from A to B, and then if it is from B to A we will get negative result. Okay. So, let us discuss the distribution of shear stress in such cross sections, and we can actually have analytical formula. So, let us try to derive those formula. So, suppose that we have this beam which has thin cross section. So, the cross section is, let us say, something like this. Okay. So, basically the cross section has got this curved shape, and then we have the x axis along the axis of the beam, we have y axis, and we also have z axis, all right. And then in the cross section we have got y axis and z axis, and since we know that the shear flows from one end to the other, we can define an arc length along the cross section. So, suppose that we run an arc length coordinate starting from one end and denoted by S. Okay. So, in this case then shear stress is only going to vary as S changes for a given S. So, for a given S we have these points, and everywhere along these points we know that shear stress is in the direction along the boundary of the cross section, and then it is also uniform along that line. because there is no space for variation. So, now you see this is x plane, the cross section is x plane, and then the arc length S, the cross section is pointing in the direction tangent to the arc length, right. So, we can think of denoting tau, the shear stress, with tau S x, is not it. So, x is for the plane and S is for the direction, and then this tau S x is only going to be function of x and S. So, for example, if you think of this line, it is not going to vary along this line, it is going to be the same. So, tau S x is simply a function of x, that means what cross section we are looking at, and S, that means where in the cross section we are looking at, all right. So, to find the formula for tau S x, we are again going to carve out a small element from the entire beam, and in this case we again take a green element which is something like this. So, we have this green element, okay. So, let us take out this green part from the beam and draw a free body diagram. Okay. So, what are the various planes on which we have traction acting? So, we have this plane which is the x plane, but as it is a right end. So, this would be at x plus delta x, and then this part is the negative x plane, and this is at the location x along the beam. Okay. So, this length of this green element is delta x, just as we had earlier. And then what can we say about this bottom face right here? So, this face is called S plane, because the normal to that plane is in the direction tangent to the arc length. So, we call it S plane. It is neither y plane nor z plane, it is S plane, okay. Because so you can remember that arc length was running from one end of the cross section, and this is your S. So, we have the S plane. Now, let us find out the total force in the x direction as earlier. Total force on the green element in x direction. So, on the x plane we have sigma x x, is not it, the bending stress, in the x direction. Likewise, on the negative x plane also we have sigma x x, and on the s plane we have tau x s. Now, you see this is positive s plane, it is not negative s plane, it is positive s plane. So, on positive s plane tau x s should point in the positive x direction. So, therefore, the shear stress here is going to point in the positive x direction. Contrast this with our earlier analysis. The bottom plane was a negative y plane, and therefore, tau x y was pointing in the negative x direction, but here it is going to point in the positive x direction. Okay. All right. So, with these tractions known in the x direction, we can now do the total force balance. Also notice, what about this surface here? So, that is on one side of the cross section, is not it? The cross section starts from that side and runs to the other side. So, that side is actually traction free, we are not applying anything on that face. So, we have no traction here. So, therefore, that part does not contribute in total force. Okay. All right. So, coming back, we do the total force balance. So, first for the x plane, so we have integration over the x plane of sigma x x at x plus delta x, comma any point in this cross section. So, that will have y and z coordinate, right, minus sigma x x at x comma y comma z, and then this whole thing gets multiplied with dA. Okay. And then we also have the S plane. So, on the S plane, we have tau x s, and this is a function of zeta, the x coordinate, we have to denote it with zeta. So, it starts from here and any point that is zeta. So, this is your x and that is your x plus delta x. So, the difference is delta x, and any arbitrary point here that is denoted by zeta. So, tau x s is a function of zeta, and then what other thing? Also the point S where we are locating the arc length, and then along the thickness we simply said that it is not varying because it is so small, is not it. So, this into dA, and this should be equal to 0. Okay. So, let us work it out. Now, as earlier, we could take this green element of any size. So, this delta x could be arbitrary. So, why do not we divide this whole thing by delta x and take the limit as delta x goes to 0. Okay. So, we divide this whole thing by delta x and this also by delta x, and then take the limit as delta x goes to 0. So, you can see that the first term gives you the derivative of sigma x x. So, we have integration over the x plane sigma x x prime of x comma y comma z dA plus, now the second integral here, you see it is over the S plane. So, it has two integrations, one is along the x and the other one is in the thickness. The one in the thickness can be carried out easily, because we said that the shear stress does not vary along the thickness. So, we get, let us say, some thickness T as a function of S. So, it is T s. So, basically the thickness here, that is T s. So, T s could be changing. So, we have T s and then integration from x to x plus delta x tau x s zeta comma s d zeta, and then we also divide by delta x and take the limit as delta x goes to 0 and this is equal to 0. So, finally, we have integration over the x plane sigma x x prime of x y z dA plus T s into, so as you can see this integral, when you work out the limit, it is simply tau x s of x comma s, and that is equal to 0. So, this implies tau x s of x comma s is minus of 1 by T s integration over the x plane of sigma x x prime x y z dA. Okay. Now, let us plug in the formula for sigma x x. So, recall when we are doing the bending of unsymmetrical beam, we found out the general formula for sigma x x. See, it is right here, this formula. So, in this formula, what is the function of x? So, it is m z, which could be varying with x, and m y, which could also be varying with x. Rest all, they are not functions of x. I y y, I y z, I z z. If your beam is such that the cross section is not changing, then I y y, I y z and I z z, they do not change with x. But m z and m y, the moment that is acting in the cross section, they would only be changing with x. So, when we find out sigma x x prime, we only take the derivative of m z and m y. Okay. So, we go back and plug in the formula for sigma x x prime. So, this becomes minus 1 by T s and then integration over the x plane m z prime into y times I y y minus z times I y z, right, plus m y prime into y times I y z minus z times I z z, and then this whole thing is divided by I y z whole square minus I y y into I z z into dA. Okay. So, now we have to find out what is mz prime and my prime. So, we had found out earlier that dmz by dx is actually minus v of y, the shear force in the y direction. So, dmz by dx is minus v of y, and dmy by dx, which we did not find out, but this will turn out to be v of z. So, shear force in y direction induces movement in the z direction, whereas shear force in the z direction induces movement in the y direction. Okay. So, these two formulas, they are not so difficult to derive, and we had actually derived the first one, second one can also be derived easily. Alright. So, we can plug it back in the formula here, and then we get this as minus 1 by T s and integration over the x plane minus V y into y times I y y minus z times I y z plus V z into y times I y z minus z times I z z divided by I y z whole square minus I y y I z z into d a. Okay. So, now in this integration we have things which are functions of y and z and quantities which are constant or only change with x, they are going to act as a constant. So, we can take it out of the integral, right. So, we will have finally minus 1 by T s into 1 over I y z whole square minus I y y into I z z, and then the integrations. You see, we have integral y d a, and what is the x plane? So, recall it is not the entire cross section, it is only going to run from 0 to s. So, it only runs from 0 to s, and then this is the shaded area, that is the x plane here, and we have integral y d a. So, that is the y centroid of this shaded cross section times the area. For example, when we have integral y d a, let us denote it by q of y, and integral z d a, let us denote that by q of z, but only for the shaded area. Okay. So, this is y bar of the shaded area times the area, and this is z bar of the shaded area times the area, where y bar and z bar are the centroids of the shaded area. Okay. So, when we plug in this formula here, we have minus V y into q y times I y y minus q z times I y z plus V z into q y times I y z minus q z times I z z. Okay. So, this is again a very messy formula, because we have an unsymmetrical cross section, but let us try to find out a special situation. What if our y and z axis are aligned along the principal axis? Okay. So, if y and z axis are aligned along the principal axis. So, this implies I y z is 0 by definition. So, we can go back to the formula and then we get tau x s as a function of x comma s, that is equal to 1 by I y y I z z into T s into, then we have minus V y q y I y y minus V z q z I z z, which we could also simplify further as minus V y q y over I z z times T s minus V z q z over I y y T s. Okay. And again, if V z is 0, then we have the formula as minus of V q by I t. Can you recall earlier we had tau equal to V q by I t, but now we have minus. You see this, we have a minus sign here. And what is the reason? It is simply because tau x s is now for the s plane. On the s plane, it is pointing in the positive x direction. Earlier, it was for the negative y plane, therefore, it was pointing in the negative x direction. So, we have a difference of minus sign now. Okay. So, this is how you can find out shear stress distribution in thin and open cross sections. Okay. So, with this I am going to close my lecture today, and in the next class we will talk about shear center and also solve some problems on bending of beams. Thank you.